which was very long. So I'm going to go a little faster on my slides. Sorry to not be able to be there in person. I do have my Zoom background, which is from Istanbul. It's a picture I took from the ferry from Üsküdar to Beşiktaş. Okay, so this morning or this afternoon rather, sorry, I want to talk to you about 6G, and in particular, I'm going to try to convince you that for the next generation and beyond, we'd like to connect with a purpose in order to efficiently use wireless resources. So for me and my students are all at Ohio State, and this is our lab, Inspire. So here's our, or I guess everybody's 2030 vision, extreme connectivity, AI nativity, and mobile 3D connectivity with smart cities, smart connected everything. That takes a lot, but it is a vision that isn't necessarily new. It's been coming for a number of generations, but for the first time, it actually has a chance to materialize, as shown here. For me, 6G is a revolution rather than an evolution, which we've seen in the previous generation, more of a sort of a evolution of 4G data services into faster services. For me, 6G is a revolution for two reasons. I've kind of divided this into this hexagon into two sides, and I want to tell you about one example from each side in today's talk. One thing that's special that we haven't considered before is human-centric connectivity. That is to say, rather than simply thinking about throughput and delay, we're for the first time thinking, how should we design the system in order to achieve a goal, in order to achieve a task with the quality of service requirement. And that brings in new metrics, for example, age of information, quality of information, related metrics or value of information. So those come on top of the traditional metrics, such as throughput and delay. The other interesting thing that I'm going to tell you about that includes AI nativity is semantic communications. So we're going to get into that a little bit. On the right-hand side is convergent connectivity. This is something that started to happen with the devices getting more and more sophisticated with communication and computing, converging a little bit, but really we're looking at systems that integrate multiple functions and designed as such. For example, sensing and communications, again, computing and communications, learning and communications. And in particular, I'm going to give an example where an edge network, a wireless edge network, can facilitate a learning process. So those are the two that we're going to look at for the rest of the hour. And with that, I want to start with the second, with the right-hand side, joint or convergent networks. So this is a part of a vision of an intelligence enabled by a network, and in particular, an edge network. So the notion of an edge network being part or facilitating learning is not new. In fact, it goes back many decades in the form of distributed learning, and more recently in 2016-17 timeframe, it was popularized by Google from a computer science perspective. with the particular form called federated learning, where a server orchestrates edge devices to do a collaborative machine learning task such as model training. So we're going to look into that a little bit. Federated learning, as I mentioned, allows the edge devices to participate and in fact enable model training in an iterative process where each device trains on its own data and then sends a model update to a server, and then the server does an aggregation, and after this computation process announces a new model, and each device then trains again until convergence. So that's the way I described it. You can already see that it is a model that has some communication overhead because of the number of rounds that you have and potentially a large number of devices that participate on this. Currently, we have Google Keyboard and such that actually uses federated learning in order to assist with writing on your phone and so forth. And it does include all this communication back and forth between the model updates. So that communication overhead has been a challenge for large-scale deployment in different scenarios. And the way that this distributed learning paradigm has been designed is agnostic to the medium underneath. So in other words, you have a channel available to send your updates. That's all that matters. Underneath, whether you have a wireless network or whether you have whatever network you have, doesn't quite matter. So that's the sort of the nominal design. And then the other one that's a main challenge is that even though federated learning itself has been first advertised as a new paradigm that protects privacy, and to a degree that's true because rather than sending your local data, say sending your pictures on your phone to a central entity to train a machine learning model, you actually train locally and then send a function of your local data in the form of your model into the server. As soon as I said function of data, you should already be thinking that indeed there's some privacy leakage, even if it's not as much as the raw data. So that has been a challenge. And again, I want to remind you that the nominal federated learning setup is agnostic to the medium underneath. So what I want to try to convince you in the next 10 minutes or so is that paying attention to the underneath medium, in this case wireless, actually helps alleviate both of these challenges. So if we know that we are wirelessly connecting to learn as opposed to simply connect, we can, in fact, take advantage of the medium itself. There's a very prominent feature of the wireless medium. It's an open medium. Electromagnetic waves aggregate and superpose naturally when they're sent simultaneously. So this open medium allows naturally the model to aggregate. We can utilize this for communication efficiency. In addition, again, the same notion that the medium is open can allow us to improve privacy. So I'm just going to give an example of this as well. These come in the form of so-called over-the-air federated learning, which is to say that we are allowing simultaneous transmissions. Simultaneous transmissions of model updates by all the edge devices, exploiting the superposition property We call this the multiple access channel. But here the notion is not our typical multiple access channel where users are sending messages which are often independent, but rather a correlated multiple access channel where the users end up correlated through these model updates that they receive from the server that they iterate on, even if they start with independent data. Luckily, we're not really that much interested in the underlying information theoretic problem, which is not easy, but really the fact that this aggregation occurs and that it can truly improve the communication efficiency. So if you have a single wireless channel, and if you can loosely synchronize and adjust your transmissions, then you don't need n times the channels. You can simply utilize the same ones. Noting that by design, what you want to recover at your edge server is the sum of these models, not the individual ones. So this is really integration of communication and computation at its best, and it's communication efficient. It goes back 5 years. I've noted here a reference that's one of the pioneers of this approach by Amiri and Gündüz from 2020. So what we brought to this approach is to bring in really learning at the outset. So as I mentioned, it's clearly a communication efficient paradigm, and you can design this sort of a little bit disjoint from the learning algorithm, right? So underlying, in fact, you can have any distributed learning algorithm that needs some kind of model aggregation or update aggregation, I should say, and you can utilize over the air federated settings. We wanted to pay attention to the fact that rather than efficient communication, our goal here is accurate learning of the model. So if we start with the goal of learning, and look into what the performance metric ought to be there, and go from there after the learning analysis to come back to the physical layer design, that is in fact the true integrated design of the communication and learning system. So in this work, that's what we have done. Rather than computation and communication, in effect, separately optimized, we've come up with this design that analyzes the learning performance, upper bounds, the distance from the optimal point, and then looking at that upper bound comes back and actually designs the physical layer in the form of what needs to be sent, how many local computation steps need to be taken, and the associated transmit power. So that's what we call adaptive over-the-air federated learning, and we have extended that afterwards. And this is sort of coming to the vision that I showed you at the beginning, to a 6G vision setting, where we can have so-called programmable channels. I call these programmable channels because channel in a communication system, in a sort of nominal communication setting, that's sort of the part of the system that we can't quite handle, other than dealing with the errors that it induces. With this new vision of 3D mobility, with UAVs going around, or even higher altitude objects going around, providing connectivity, we effectively have come to a realization of a channel setting where we can manipulate the channels. Similarly, I'm going to give an example from intelligent surfaces. These are new elements that we can introduce to our network that could reflect favorably as we want the signal, so that, again, to a degree, making channels more favorable. So if we bring this is a purely physical layer phenomenon. If we bring this into this learning problem, we might be able to do even better. And what I mean by bringing this physical layer design, even with the previous one, into the learning network, I mean bringing it into the algorithm design itself. So facilitating learning by programming the propagation environment better is an exciting 6G and beyond direction. So in this sense, we've adopted this RIS into our network, first a single one, and provided a cross-layer framework to unify communication and learning. And so we end up with an iterative algorithm that not only updates the model weights and the transmit power and the computation steps, but also accordingly this reflecting intelligent surface coefficients or mirrors. So the phase adjustments of those also come into each of the global round to program the channel accordingly. While the work is for passive RAS, of course, the idea can be applied to other types of reflecting surfaces or any other new element that can program the channel accordingly. So the idea is to include a step in your global round for the new channel update, if you like. Just a very quick numerical comparison. So this is the improved designs that I mentioned. I would say from the learning perspective rather than communication perspective, compared to the state of the art, where a number of let's say realistic constraints render your learning algorithm pretty useless. So you can see the state of the art failing to learn in this 10 class data set, whereas ours actually have present a reasonably good performance. Okay, this notion can also be, so this is rather new from the communication perspective as well. Rather than one large collection of mirrors in this reflective surface, you can imagine that each phone might have a small personal RAS associated with it. And if we allow this allows, in a sense, personalization of this programmability of your medium, and that brings in improved performance and being able to personalize models to users, individual users or groups of users. So personalized learning, personalized federated learning, again, you can utilize multitask learning type of frameworks to bring this in to this wireless setting, and again design a distributed federated learning algorithm that includes this physical layer programmability into the learning itself. Here is a non-convex objective, and you can see the test accuracy with the personalized models to be superior to all of the state-of-the-art personalized ones. So we've seen the communication efficiency part. I promised you that I would talk about privacy as well. And so, as briefly mentioned before, these federated learning paradigms allow local training with local data, so you don't have to send your data to a central server, but you do have to send your model updates, which is a function of the data, which eventually leaks information about the data itself, user, etc. A typical, or one of the main ways of securing or making this private is differential privacy. And at the heart of it, although there's the math behind it suggests this, of course, at the heart of it, the differential privacy algorithm is one that essentially adds noise before introducing the update. So as such, we have the in the setting that we have without or agnostic to the medium, we have the mechanism, differential privacy mechanism, that actually adds noise before sending an update to the edge server. So when we look at this as communication theories, as wireless communications researchers, of course, the first thing that comes to mind, really for any medium, but of course, in particular, in a medium that can do model aggregation naturally over the air, is this additive noise that we have. So we have additive noise in every wireless communication system. So if we're if we're implementing this over wireless, over the air federated learning, then we can simply utilize this channel noise to the degree that it can be helpful in differential privacy as well. So rather than noise, adding noise to our updates and then trying to remove the channel noise, but trying to decode the noisified or noised versions of the updates, we can simply utilize the channel noise and kind of get away with it. And if that's not enough, if the level is not enough that's available in the channel, then we can actually utilize a terminal to chime in and contribute to this by sending noise to make sure that we have the level of privacy needed. And so that's the notion of differentially private over-the-air federated learning. The mechanism, as I mentioned, is to utilize the natural noise that exists in the wireless channel. And if that's not enough for the privacy requirements, then a cooperative jammer can be employed in the network to send noise and noisify the updates. So this is a very quick, again, an experimental result comparing with the state of the art, which looks into this notion of using the channel noise, but again goes with more of a non-adaptive version of the over-the-air federated learning. So as you can see, we're doing better by jointly optimizing everything. Okay, so that's very quickly what I wanted to tell you about the first example. I'm going to move to the second one. Remember that one of the exciting directions in 6G is the human-centric connectivity, and that brings us to this new paradigm of connecting to convey the meaning. We call this semantic communications. Simply put, rather than designing a communication system for reliability of a digital sequence without paying attention to what the content is, our goal now is to preserve, to the best of our ability, the meaning of what is meant to be sent, if you like. So this way we can leverage the redundancy in language, and we can utilize in a practical manner, the notion of context and the ambiguity without the context to have, in fact, more efficient connectivity. So the classical communication system consists of a transmitter-receiver with a channel in between, and a semantic communication system consists of a semantic transmitter, semantic receiver, and a channel in between. So really, at least this incarnation, the physical channel is there. We're simply replacing the transmitter and receiver, where the transmitter extracts semantic features and sends an efficient transmission, and the receiver decodes these to either reconstruct the message or its likeness, semantic likeness, or a version of it that is useful for the task at hand. So this does pair well with so-called task-oriented or goal-oriented settings. So this is a paper. I want to go back a little bit. We started thinking about this problem about 15 years ago. This sort of new idea of trying to get the meaning of the messages into the communication design itself. This predates, predates the machine learning craze that had happened. So it's a modest paper from way back when, where a former student of mine, Başak, who is now an assistant professor in UC Riverside, and I thought about this problem and said we need to start with the right metric. And that metric is different than the metric that we've seen up to date, which is really the metric of a syntactic metric of, say, error rate of communication bits or packets, if you like. So we designed a metric called semantic distortion. And so the goal here is for a communication link to be designed not to minimize a bit error rate, but to minimize the semantic distortion. It is a physical layer problem, as it's stated here. We called it semantic assignment, semantic index assignment. The index really is the code word, the transmission code word we end up choosing. And the idea here is really to choose code words for messages, in this case words, which are the code words that are, if you like, closer, say in Hamming distance, to the code words that are closer in meaning. The idea here, and this is what came out from all the optimization, but really the idea, if you think about it, is very intuitive, and says that if you're transmitting over a noisy channel, it's likely that if you end up making an error, you're going to land in a code word that's a neighboring code word that's closest in Hamming distance. And if that neighboring code word, which is a syntactic error, is in fact semantically corresponding to the same word or something similar, then you don't need to retransmit in this setting. Even though it's a syntactic error, it's not going to be a semantic error. So that means savings for the design. So it's that simple an idea that came out of this. At the time, due to really the absence of all of this data revolution, this was not a scalable approach. It was a cute idea that could go up to a corpus of 16 words with the computational resources we had at hand, utilizing simulated annealing, and so we had this paper, and we did some additional studies on on a game theoretic setup where you could have a sort of an external influencer trying to give you context for a semantic decoding and so on. But again, it was a work that was an idea that was a little bit, it had nowhere to go. But then the machine learning revolution had happened, and deep learning came into wireless in a pervasive manner after the introduction of the autoencoder-based wireless physical layer designs. And it brought back a lot of excitement into semantic communications. This is now a very obsolete tutorial that we did we wrote back in 2022, and there's been probably thousands or more papers on semantic communications since then. But in essence, it gives you an idea of where this came from and how we can utilize various deep learning and other machine learning techniques in designing semantic communication systems. So our vision, of course, also has evolved in this 10 years. We're able to now consider multimodal communications, and from taxonomy-based distortion metrics. I'm going to give an example where we've switched to embedding-based distortion metrics in order to use the notion of context. We've used graph coloring, hypergraph coloring techniques in the original work. And of course, now we can use clustering and also for context attention mechanisms. I'm going to give an example of that too. And as I mentioned, from very limited computational methods to neural network enabled optimization. So the key here is that there could be applications where exactly construction is no longer a requirement. That's already a savings. That's already suggesting methods of compression, the ideas of compression to bring into this. And also the fact that we have structures. So introducing these methods where we could utilize the grammatical structures, the connection between the words and so on in the text context. And of course, you can think about this in other forms of communication as well, modes of communication as well. The overall idea, though, is to focus on semantic metrics rather than syntactic metrics when we design the system. I mentioned this already. It pairs well with task-oriented scenarios, where the receiver needs only the information relevant to the particular task that it needs to do. So I'm going to give an example that's semantic compression. So this is a task-oriented scenario, and the task is a classification. The idea is to minimize the semantic loss and utilize the semantic redundancies for compression. What we want, so there are a lot, as I mentioned, there are lots of works in this space as well, extracting semantic features and communicating them, typically by end-to-end deep learner autoencoder type designs. And we wanted to have a little bit of a different view on this, effectively extending upon that small paper I talked to you about from way back when, the same type of idea, but maybe without this potentially excessive training overhead. So we didn't want to use an end-to-end deep learning model for this. So we asked the question, what can we do? And started studying the recent developments in natural language processing. At the time, this large models or foundational models were just coming into the picture. Maybe a little later than this, we discovered something called ChatGPT as a species. But these are all essentially, we've looked into this notion of utilizing pre-trained models, and starting with the pre-trained models and then refining them to our purpose, if you like. How do these work? You have a very large data set that you can train offline and with extensive computational resources for certain generic tasks. And then you could utilize smaller data sets, in this case, for instance, messages that come in for more specific, for fine-tuning, if you like, with less computational resources. So, as I mentioned, large language models, as you know, work exactly like this, and really this large model has a deep understanding embedded in it, literally and figuratively, the properties of semantics. Okay, so what does that mean in this case? I'm just going to give the example that we used. So this is a vision and text model, a pre-trained model. So you have sentences and images that trains this model, and what you end up getting in the end are points in a vector space, which are called embeddings. And so the idea is that semantically speaking, if an image and a sentence is close in meaning, then they're going to be close. They're going to translate into these vectors, into these embeddings that are close in this space. So this picture and the cat that's on the mat are close together, but something like "I have a blue car" is quite far away. Not unlike the ideas that came about from the little paper that I mentioned earlier. Okay, so once we have these embeddings, then we can use these to train a neural network to actually perform downstream tasks such as classification, and importantly, at least we have numbers to deal with. So that's a lot better for engineers than dealing with sort of more blurry notions of whether this is similar to this and what does it mean and so forth. So these are also, as you know, a paradigm shift for NLP as well, because rather than having a human tell you whether this picture is good or not, or whether this thing is similar to this or not, and labeling manually, these actually do these automatic embeddings, which has in fact revolutionized the entire field of NLP. Okay, so what do we do with these? So we have now these embeddings. We have the embeddings of the sentences or the pictures or a mixture thereof. What do we do with this? We have vectors that are continuous valued. If we want to send those in a digital manner, we have to start quantizing with quantizing. So that's what we do. The first method is so-called semantic quantization. We start with a code book with randomly chosen embeddings from the data set. And then when a new sample when we get a new sample, then we map it to a code word from this code book. And we can actually use a deep learner to optimize that. So that's the fine-tuning part. And so that's a method for you to end up with a digital correspondence for your message. And then you can send it. You can do even better. You can use a clustering algorithm to cluster your points and construct the codebook that way. And so that's another machine learning aided construction of a code book, and then you can send your messages accordingly. In either case, I want to clarify the departure from the sort of the autoencoder-based models where you get a joint source channel code that's an analog transmission versus this approach, which you effectively get your embeddings, you turn them into digital messages, and then you can simply put an error correction code on top of it and send through the channel. So this is if you like, backward compatible. This is what is being done currently in the systems, right? So you have a source code, and then you have a channel code, and then you simply send your message digitally. So this is conforming to that, simply replacing your source coder, if you like, with a semantic source code. Okay, so what do we get from this? So this is without the channel part, simply to show the savings that we get with our approaches. And you see a 2 orders of magnitude savings with reasonably good accuracies. So somewhat compatible. So we've tried this on a large number of data sets, and you can see that our approaches are doing reasonably well with 2 orders of magnitude less transmissions bits. As I mentioned, you can also put a standard error correction code on it, and then just send it through a wireless channel. Here you see the comparison with autoencoder approaches, which are doing similarly at reasonable SNRs, I would say about 10 dB. What's important is that if you look at this metric, so this is the metric we defined in this paper, the metric is simply the following. If I give you a time budget, how many correct classifications can you give me in that time budget? So I give you, 5 seconds. In that 5 seconds, your wireless channel can change. You may have to retrain, or you may have to train at least once, et cetera, et cetera. With the conventional approaches, and with our approach, you simply start with the embeddings. So here you see again the 2 orders of magnitude about advantage that we end up having with these approaches. Okay, so we can utilize pre-training models to do digital semantic communications, and we can execute a task at the receiver end. In that example, it was classification. We can also, even if we have to do reconstruction, we can also utilize semantic ideas and the meanings, conveying the meanings to do better. How do we decode messages semantically? We've looked into this in the context of text and utilized attention mechanisms in both encoding and decoding. Attention mechanisms provide context in encoding and decoding, so creates context-aware embeddings. Again, these vectors. So in this case, something like riverbank and bank account would create different embeddings because of the context. Same thing at the receiver. You have the context, which really is the side information, and that context allows you to decode correctly, which in this case is a grammatical connection in this example. Okay, so recently we've looked into this with 2 of my students. By the way, I have an international group, but somehow, I guess the federated learning is not done by a Turkish student. But anyway, so as it turns out, the examples I've been giving is with Turkish students. Anyway, so we've looked into cooperative network, a 3-node relay network, and utilized token-level communications with semantic-aware relaying, where we introduced 2 methods. One is what we call semantic lossy forwarding. So it's some form of decode and forward with semantics. And the other one is semantic predict and forward, where the relay can predict the next token, utilizing a transformer architecture and creating context-aware embeddings. What do I mean by semantically aware relaying? You can kind of see an example here. The source broadcasts the word well, or what corresponds to it. The relay, because of the message, because of the noise in the channel, receives it as good, and the destination as fine. The relay then does the processing, semantic processing, with context awareness, and corrects it when forwarding, and the destination now has using also potentially its context-aware processing corrected as well. Okay, so that's the idea, and very recently, we just presented this in ICC this month. We've extended this notion to semantic sentence forwarding. So this is where, again, our wireless engineering hat plays a role. Currently, all of the large language models are based on tokens. Tokens are words or parts of words, essentially, and contexts are created, but it's not a very long memory at the moment. So because there are abundance of computational resources and time, and the models could be really infinitely large, you don't have to be super efficient, and you do really well, as we know. When you're in a wireless setting, you have to think about efficiency first. So token by token communication can be improved by grouping the tokens into constructing units that have meanings by themselves, and those are sentences. So we've looked into those, or that kind of a setting, and actually provided even more efficient results. With the token versus semantic level encoding, what I mean is different sentences could represent the similar thing, even though they have different number of words. So that means that we can convert them into same number of embeddings that way. A single embedding that really represents the meaning of the sentence, and that helps in our communication. Same thing with decoding. We don't have to decode the same number of tokens, both sentences actually, even though they have different number of quote unquote tokens, they translate into one token that can be decoded as such. And so here's an example of sentence level semantic relaying. The source sends, please respond quickly. Because of the channel and the noise, the relay gets quick responses are appreciated, and destination gets swift responses are valued. And using the context, the relay can correct, and then we can actually reconstruct what we want. So this is an exact reconstruction example. Lastly, in the 1 minute I have, I'm going to show you the results, but I just want to note that there are standard metrics in evaluating semantic similarity, which we have used, but then in examining those, we've noted that they have some deficiencies. So, for example, the standard semantic similarity metric between sentences, SBERT, comes up with the 0.5 for these two sentences, I hate you and I love you, which are clearly opposite of meaning. And then you can see another example below where, the meaning is completely different, but somehow the similarity is there because the words are pretty much the same. So my students did something that I don't usually advise my students to do, which is they actually fed all of these and said, to ChatGPT, can you construct a better metric for us? And turns out it could. So we have the GPT-based semantic similarity metric that we have also used in this work to compare, which we believe it to a more accurate representation of sentiments of the sentences. You can see that our approaches are doing better than the syntactic approaches significantly. And I want to just show you this last one to provide you the insight that research constraints scenarios are a good ground for semantically encoding a sentence because we get better data compression and we get more semantic robustness out of this. So in conclusion, I hope I've been able to convince you that 6G is a revolution and it's a playground for researchers. Given that everything is programmable, there's a much shorter window for research ideas from even theory to come into practice, and we can continue to utilize this very special medium, wireless medium, to get better learning performance as well as better security and privacy. And AI native wireless is, when used properly with the resources of wireless in mind, could be a game changer. And as mentioned before in the title, I believe it's time for connecting with purpose. And with that, I'd like to thank you very much for listening.
Only a small part of the applauding reached you, perhaps, because I'm closer to the mic. Thank you very much for this wonderful talk, taking us through many dimensions of recent developments in wireless communications and beyond. So if you don't mind, maybe I can switch to Turkish. I don't know. Are there any questions from the crowd? Let me first continue in English with questions, and then maybe we will wrap up in Turkish again. Questions?
That's a good question. I think people are just starting to talk about this and starting to take this seriously. So we honestly don't know if it's going to make it to 6G. But I think the 3GPP is going to release their findings soon. And this is being talked about, maybe not as seriously as integrated sensing and communications, that's clearly in. But I'm hoping maybe in an advanced version, it will be there in some form.
Yeah, Mona's presentation in the morning, Mona Gassemian is here. So I remember seeing stuff related to semantics, although they may not have been coined exactly that way. But the idea is surely there. I'm hoping that it will go into standards. Any other questions? I have several, but I'm going to ask one, if you allow me. So in one of the slides, in one of these recent works, you had this differentiation between semantic compression and semantic quantization. And I couldn't help but think, if something is semantic, isn't quantization equivalent to compression in some sense, because it's semantic?
Oh, absolutely. These are all, these are just namings of different methods that we introduce. So quantization is what we have to do, and that's already lossy compression, if you like, between those constellation points that we already chose and what's coming in. And then the other one is sort of automatic. Rather than choosing a random code book, sticking to it, the other one simply automatically groups what's coming into a code book and then choosing the cluster point. So they're both definitely compression methods and quantization methods at the same time. They're just a little different from one another.
Yeah, I was thinking maybe the compression could have been part of the semantic, maybe the sampling, sparse sampling in the beginning, the way you actually choose your metrics in the first place.
The code book, you mean?
Yeah. The selection of the codebook in the beginning itself,
right,
could have been part of.
Good.
Form of source coding, perhaps. Yeah. In any case,
this is all. This can also be. Yes, this can all be considered as source coding. The difference is we don't have. We don't have an IID source. We don't have a market. We don't assume any kind of form. We simply take the embeddings, which have some underlying structure that we don't know, which is why starting with a random code book works.
Okay. Any further questions to Professor Yener? Yeah, I do not see any. So we will let you rest then until your next 26 meetings today.
Thank you very much for çok teşekkürler. Evet. Çok teşekkürler davet için.
Evet, Aylin Hoca'ya gerçekten çok teşekkür ediyoruz. Çok busy bir schedule içerisinde. Bugün sabah bir e-mail attım. Zoom linkini yanıt olarak 2 hafta içerisinde cevap vermezsem bana tekrar e-mail atın diye bir şey geldi. Çok teşekkürler bizimle birlikte olduğu için. Ben bir tekrar alkış rica ediyorum kendisi için. Bir de bir şey göstereceğim müsaade ederseniz. Alan Oppenheim'la ortak bir yanınız var. Dün aynısını ona da yaptık. Burada olamadığınız için sizin için hazırladığımız teşekkür belgelerimiz, kristallerimiz var. Şöyle yaklaştırıp.
Çok güzel, çok teşekkür ederim. Çok teşekkür ederim. Bir dahaki İstanbul'a geldiğimde muhakkak alıp.
Ellerimle teslim edeceğim geldiğinizde.
Evet, ben de ofisime koyduğuma dair sana gönderirim.
Tamam.
Çok teşekkürler.
Teşekkür ediyoruz.
İyi bir seminer diliyorum. Hoşça kalın.
Sağ olun. Hoşça kalın.
İyi günler.